Anyway, so welcome to image captioning. I'm Jessica.
I'm Richa. And I'm Ashna.
So what are we doing with attention-based image captioning? So essentially, long story short, well, long story, we're taking an image and we're creating a caption out of that. And it's not just like boxes, you know, like, hey, here's a flower, here's a person, here's a wave. No, we're not just making boxes. We're making an actual sentence. A readable sentence that a child could pronounce it at maybe a young age, maybe like, 2, 3, when they don't know their vocabulary. But the attention-based section will also tell us where the computer is taking these images of. So it won't say, here's the rose. It'll be like, this is where I've gotten the word rose. Essentially, we're telling the AI, hey, here's an image. Tell us what is happening here. The neural network is the basis of our project. It is a very large part of this. So what is it really? You've heard this a million times. I guess here's the crash course. So envision the human mind. It's called the neural network for a reason. In our mind, we have neurons that send signals to each other that tells the body what to do. Well, the neural network is a network of neurons for the computer. So the computer's neurons, also known as the nodes, will pass signals to each other and take the data, which is their input layer, and send it into the next layer, which it will then use a function such as weights and biases to change it up, and it will keep going and keep going until it reaches the output. That's the basics. So not all data is linear, so these functions aren't just your usual mx plus b is equal to y. It also includes nonlinear functions such as sigmoids, which if you don't know what a sigmoid is, imagine a sideways squiggle and you've pretty much gotten about it. In the end, once the data has emerged from the network, we have our classifications. In our project, we actually use two different neural networks. We use the RNN and the CNN, or the recurrent, which will allow us to move backwards. So we don't have to go from just input to output. We can also now go from output to input. And we can also use the CNN, which is the convolutional neural network, which helps us with classifying images, because there's a reason this is called image-based captioning and not just text. Matrices. No one likes matrices, but that's okay. They're a vital part of this. With matrices, both text and images are created into matrices. Text specifically, we will go into one hot later. With images, however, you can look at it. So with images, each pixel, correct? So you have your black and your white, and you have, if you want to go with your black and white, each matrix or 2D list is essentially how intense is that black? Is that like the darkest black you've ever seen? Or is that like, I can't see it at all? Color images are a bit different, however, and so they're 3D lists instead, because you've got multiple colors, because, unfortunately there's no function for just like one number of pink. We can also use multiple functions with matrices, such as multiplication, as you see right there. Math is fun. It's not. Or we can add the matrices together depending on how many rows and how many columns. That's a math lesson. This is CS. NumPy. NumPy, or as they said, NumP. Essentially, so it's a fundamental package for scientific computing in Python. So it's used to handle these matrices in Python. If without it, we'd kind of be lost, so we kind of need this here. So essentially, here is some different ways that we've used NumPy. For example, here is our functions. This is actually the output for a bunch of different matrices, as well as multiplications down here. And that's how you input your matrices. Next, we have our OpenCV, which, as said before, this is what we use to handle the images in Python, which we also need because we're working with images. So as you can see here, this is actually the output you get for an image if you were to input it. Bunch of numbers, all of this is black. And so you can manipulate the images as well. So this is what's being printed out in the first place. After color correction, you'll get the blue version of the Pokemon. And then if you really want it, you can go grayscale. And so relations to this project with both images and text are represented in matrices. Without them, you can't go through the neural network, because we need these functions, we need to be able to manipulate these matrices, and we need to be able to take it from our data and actually turn them into numbers. So by using both the matrix multiplication, or in our case, matrix addition, and the neural network, we can classify the images after, a bit of training.
Okay, so the neural network process, like how to train a model. So for this instance, we're just gonna train a model to tell us the probability of like every word in a vocabulary being like close to the next word or close to a certain word. So the process is first you do data preparation, and that's when you get all of your data and you kind of split it up. And then you do initialization is when you do like your word embeddings, which I'll explain later, and you create your first model. And then you do forward propagation, which is just going through your model and putting in your data to get a predicted y value. And then you do your loss function, which is just comparing your actual y value from your labels to your predicted one. And then you do back propagation, which is going backward through the neural network the same way, and updating your weights. And then you do evaluation, which is just like plotting over time your loss compared to how many times you've run through it. Okay, so data preparation for this. So first you tokenize the text, which is like you're given a corpus, which is basically just like a sentence, and you tokenize it, which means splitting it into words. You can kind of like see the boxes over in that image. And you define a window size. So for over there, you can see the window size is 2. So the blue word is the word you're looking at, and then you go 2 over both ways. So all of the boxed words are your window size. And then you get your training data, which is like each word that you're looking at with the ones in the window size of the training samples. And then when we were doing it, we used a lot of one-hot encoding, which is basically just a way to turn categorical data into numerical data and like binary. So we have like, for instance, 3 categories, red, green, and blue, and we put them into their own vectors, and we put like a 1 in the position of whatever category it is. So like red will be 1, 0, 0, green is 0, 1, 0, and blue is 0, 0, 1. Okay, so initialization is when we initialize your word embeddings and like initialize your model by setting up weights, which are like the parameters for each model. So we use word to vec, which is like a shallow neural network, so it doesn't really have too many layers. But it has an input layer, which is where you send in your like words in your sentence. A hidden layer is like when you put the operations on it, and then output layer, which is going to send out your word embedding. And a word embedding is like a real number vector representation of a word, and the dimensions of a word embedding are vocab size by embedding size. So if you look at that picture over there, it's kind of like an image of a word embedding. So the vocabulary is I love dogs, so the vocab size is 3 because there's 3 words. So if you look at I love dogs, so each of them have their own column. So there's 3 columns because of vocab size, and embedding size is how many ever like long you want the vector for each word to be. So it's flipped from like what we actually did. So just imagine like the words on the left and the embedding size on the top. And then the dense layer is like something else you're setting up during initialization. It's just like a layer of neurons to pass your data through, and it's called dense layer because it's fully connected. So each neuron in the dense layer is connected to each one in the next layer. And the dimensions for that are embedding size by vocab size. So it's the opposite of word embedding. So at the outputs of both of those, you can multiply them together because the column size and the row size are the same. Okay, forward propagation. So that's just how neural networks make predictions because you send your data through your neural network. So this is just like an example. So you're given an input x and an output y. Those are over there. And then you multiply by your weight. So in this case, the weights are theta. So you multiply x by theta to get your next layer, and then you put, when you multiply x by theta, you get that one on the bottom left, and your activation function is f of x equals 2x. So you put that on this output, and you get that one in the bottom right corner. And then for your next layer, that one in the bottom right corner kind of just like becomes your new input, and then you multiply it by like a new set of weights and put a new activation function on it, and then you get what you have. And then you, in the end, you put like a softmax function. So that just applies a normal distribution, which is like statistics, I guess. You just kind of make the mean of your data 0 and you put it with a standard deviation of 1. And from that, you can calculate like probabilities using statistics. Okay, so the loss function, backpropagation, and evaluate. So the loss function isn't too challenging of a concept. It's basically just creating, getting the difference of your predicted and actual Y output. So just checking how good your model did. And then backpropagation is how we're improving the model. So you're going back through it. You start with the softmax, and you subtract your actual Y values from your softmax values. And you find the new weights going backwards. So you go through the hidden layer and find those new weights, and then you get the new weights from your input layer. And then when you're going through your model again for the next time, you will use those new weights, and hopefully your loss will like decrease. And that's basically what evaluate is. You'll plot epochs, which is like the number of times you want to go through your model, against your loss. So hopefully that should be decreasing because you want your loss to get smaller.
Okay, so using all the information that Richard just went over, kind of implemented this into TensorFlow, which is a program that helps build models out of data. So we used TensorFlow first to train a neural network. So what we did is we loaded sample data from this Bashan-Vincent data set, which basically gave us a bunch of images. You can't really see it, but it's like a bunch of images of shoes, a bunch of images of shirts, and all these different things like sandals, coats. And they were all given to us in 28 by 28 numpy arrays with pixel values ranging between 0 to 255. And then they were all labeled with a float between 0 and 9. So they were either labeled as like, so all the shoes, as you can see at the bottom, were all labeled with like a 9 because they're all ankle boots. So what we did is we first had to, so we first had to build our model. So we did this by, so I kind of drew this out. So we had 3 layers in our neural network. So our first layer, what we did is we flattened out all of our pictures of our like boots and shoes and shirts. So we had all these 28 by 28 pixels, and then like I drew an example. So like we would take the bottom and then we would like flatten it out, and then so you can see like the blue, blue, brown. So that'd be like blue, blue, brown. And then we would like do the same for each successive layer. And then we put it through our dense layer, so the dense layer is connected. And that had 128 nodes, so I could draw all 128, so I drew a couple. And then we put it through our softmax layer, which had 10 outputs, or like nodes. And then these 10 nodes, okay, so basically these 10 nodes, they just gave the probability of each one if it belonged in one of the 10 like outputs. So if we go back, so kind of it gave us an array so like this. So like some of them were like really, really small probabilities, like 1 to the 10, like 10 to the negative 22nd, that's like a really small probability. And then some of them were bigger, so like 10 to the negative first. So then we took that and we graphed it. So this is like our graph. So like shirts is like very low, but then ankle boots was like very high. So you can see that that image was an ankle boot. So then we used TensorFlow and text classification. So for that, we used an IMDb dataset that contained 50,000 movie reviews. And we used the first 25,000 for training, and then the last 25,000 for testing. So the words in the reviews had been converted to integers. So each integer, so like we have like the number 1 here represents a word. So like 1 might represent the, 30 might represent hello, I don't know. Anything, I don't really know that. And then we're all also labeled with a 0 or a 1. So 1 meant that the review was positive, and 0 meant that the review was negative. So we had to prepare the data because the movie reviews were all different lengths. And in order for data to go inside a neural network, they all have to like be the same dimensions for the array. So we did that by padding. So they went over this in the other presentation, but basically like, so this review was really small and this review was really big. And that was like one of our biggest ones. So what we had to do is we had to make them the same size. So we added a bunch of like white space. So we added all of these zeros. And then like this one, kind of medium size, we had to add some zeros. So this is like padding, and that was necessary.